purposes. Today, in this first session, I will not be covering the software part right now. In the second session, we will do that. So let me just start my presentation.
I think, sir, some kind of noise is coming from your background. Let me just check.
I request all the participants to be in mute. Yeah, you can start, sir.
Okay, fine. So some of the part Pradeep has already covered yesterday. So I'll just quickly revise that. So what is medical image processing? What is 3D medical image processing? So 3D medical image processing is nothing but converting your MRI or CT scans to a 3D model using some tool in between. Uh, to convert to the 3D models, we have to use some tools like image segmentation tools, filtering tools, morphological tools, and use these tools to convert to generate our 3D model. Image-based modeling is being adopted in many fields now, mainly because it reveals internal and external features of any anatomy, whether it be in case of medical or materials. Realistic finite element analysis and CFD codes are also developing so much that we are getting very real simulated results. And these simulations can only be done when we have a 3D model with us, finite element mesh model with us. So these tools, these softwares help us generate a finite element mesh for our region of interest. So how does simpleware software come into picture? So simpleware software offers a complete 3D image segmentation and model generation solution, from going from scans to 3D models, accurately process images, obtain measurements and statistics, and export high quality models to design, simulation, and 3D printing applications. So we will discuss in detail about these today. So any medical image processing starts from acquisition of images. Once the data is acquisition, we do processing and then further visualization and reporting. The processing part contains these subparts, which start from pre-processing, preparing our data for the 3D 3D imaging, 3D image processing, and then we have, like in pre-processing, we do things like removing noises, some noise using some filters, and cropping down to our region of interest and etc. Then we determine our region of interest by doing the segmentation of that part. After that, we detect the final part, and then we perform some analysis that can be some kind of measurements, and we prepare the results, and then for final diagnosis is done. So this is the part where simpleware comes into picture. These are different parts of the image processing workflow. And just give me a second, sir. I think I'm having some issues with my mic, I believe. Let me just change this. Just 1 second, sorry. Okay. Can you confirm now, sir, whether this is my voice correctly audible now?
Now it is audible, sir.
Okay.
So participants, please respond once is the resource person's voice is audible.
Yes, sir.
Yes, sir, it is audible.
Okay, please. Thank you.
Okay. Thank you for confirming. So now we will discuss about what are the different parts of the 3D image processing. So any 3D image processing will have at least 3 or 4 of these steps. And we will discuss about these steps one by one. So if we see in the chronological manner, the image processing will start by import and visualization of our data set, which we are getting from an MRI or CT scan. Then we can move ahead and do the segmentation and processing of our region of interest. Then we have to do some kind of analysis, like to reach our end goal, we can utilize any of these three methods. If our end goal is to see the fit of an implant in the model, so we can go ahead and do the CAD and image integration. Then we can do the measurement and analysis part. And once we are satisfied with all that, we can go ahead and generate our model for simulation purposes if that is required. So these three steps are completely interchangeable. They can be, anyone can be done first and so on. Next, we have next step comes as scripting and automation. So once we have developed a workflow and we have multiple data sets on which we want to do the same, we want to perform the same workflow, we have the option to generate scripts of our steps that we have done. So we can generate scripts in Python and C#, and we can rerun those scripts to complete all those tasks automatically. Other than that, we have some, we can generate some plugins. So let's discuss about these steps one by one. So this is our first step, which is import of any data set. So in the image here, we have imported this CT scan of the pelvic structure. So import of MRI, CT, micro-CT, confocal microscopy, FibSim, 2D image stacks, and raw image data is supported in our tool and in general image processing tools. We can register multiple data sets to get a very better view of our region of interest. For an example, if I want to segment a muscle or a soft tissue, I can co-register a CT scan and an MRI scan to get a better view of my region of interest, that is a soft tissue in this case. So that is something that we do during the import and visualization process. We can visualize the 3D rendering. In the fourth image over here, you can see this is a 3D rendering of the model that we have imported. This is shown before any kind of processing we have started. So this modeling also can be done by using very fast GPU rendering. We have wide range of image quality improvements to reduce noise, artifacts, smoothen the images. So right now in this image here, you can see this is a fairly good quality image, but sometimes we get lots of noise and pixel noise in the images. So we can use some tools present in the software to remove those kind of noises, to smoothen out our data set, to maybe have a better look at our region of interest and to assist in segmentation further. These are some of the import formats that we import in our tool. So this is the most used medical dataset format, that is DICOM. We can import DICOM tags along with it. We have DICO NDE images, which is an emerging non-destructive engineering data format. We can then import some 2D image stacks in these formats and some pixel types, raw data sets as well. In further steps, we can import CAD images in formats of STL, PLY, IGS, and STEP. Now, the second part of our workflow is doing the segmentation. So this is the most important part and the part that consumes the most of the time in the 3D image workflow, image processing workflow. So we utilize some automated, semi-automated, or completely manual tools to attain our region of interest, whatever that may be. It can be a hard tissue or soft tissue. And some of these tools are thresholdings. Thresholding is a semi-automated tool. We have region growing, flood fill tools, paint with threshold tools, and many more. So in the second session, when I will show you the GUI of the simpleware software, so you will see what tools we have for doing the segmentation. Split and merge segmentation tools are very helpful in cases where we have multiple parts. So in the first picture over here, you can see this is a pelvic structure. And in the second part, we have segmented these into multiple parts. So this is possible due to some split region tools and some along with some other tools as well. So these are some tools, an example to show what these tools do. So here you can see this is the region growing tool. Simply clicking it is iterating the tasks, the number of times we have selected. So this is one quick method to do segmentation of soft tissues. Then we have a 3D wrap tool. In a complex segmentation or a bad quality image, we utilize this tool to segment our region of interest. So it is also very helpful, although it takes more time, but it is very accurate. Next step could be measurement and analysis. Once we have generated our model, our 3D model, we can go ahead and do some kind of measurement on it, like calculating distances between 2 points, calculating the center of any bone, and diameter, and etc. So similarly, we can calculate volume, surface areas, orientations, distributions of grayscales, like seeing the bone density, etc. We can use some tools to calculate wall thickness automatically. We have center line fitting and analysis within dedicated tools. And we can assess statistics globally or in local region of interest. So this is also very helpful when we are interested in a particular part of our region of interest. That can be, in this case, head of the femur. So maybe I want to check some statistics of that part. So that can be done separately. Our next step could be in the 3D image processing workflow can be CAD and image integration. So this is also very helpful for people who are into implant design and manufacturing, you can say, or study of implant and study of interaction of implants with the human body. So this is something very useful. And what we do in this step is we import a CAD model and fit it with the anatomy. Once we fit it, we can check using several tools that how much part of it is the implant is in contact with the anatomy, whether it is fitting correctly or not, or do I need to change some parameters of the implant. So these all things we do in the CAD and image integration. We study the human device interaction. And another very helpful thing in this is we can also design implants using some third-party tools like SolidWorks in this part itself. So what we can do is we can export our anatomy. Let's say, taking example of this pelvic structure. So we can export this complete model to SolidWorks, let's say, and then what I have is measurements and actual measurements or actual size of this model in SolidWorks. Once we have that, we can design an implant very easily using some database, or we can design it from ground up. Once we have designed it, we can check the fit with the implant and make some more changes to get a much refined output. Our next step can be generation of models. So by models here, I mean finite element and CFD models specifically. So, or it can also be a surface model in case of 3D printing. So for generating finite element meshes, we need to have a robust algorithm in the background to have a very good quality finite element mesh. So that helps us in doing the simulation with more accuracy, with more configurability. So in simpleware, we can configure our model, our finite element mesh for different materials, for different boundary conditions, and different coarseness or fineness of the tetrahedral or hexahedral elements that we are going to create. Along with this, we have option to export for CFD, and in the next slide, I will just show you what exports we can do. So this is also a very important, key point in when we are exporting the model, that the model that we are exporting should be supported by the software in which I'm going to do the simulation. Let's say I'm going to do the simulation in ANSYS. So I will generate my model based on ANSYS configurations, whether ANSYS supports material characteristics in the model or not. So that is something we can do here. We can configure models based on the output that we need. These are some of the basic image export formats supported from the software. And these are some models that we can. These are some models that are for finite element mesh that we can export from here. So here we can see we can directly export to Abacus formats: Adena, ANSYS, Workbench, COMSOL Multiphysics, LS-DYNA, Nastran, Patran, some generic formats as well, then VTK and MATLAB. So just to give you an example, MATLAB doesn't support import of material characteristics. So when I select output, the export type as MATLAB in simpleware, so I will not have the option to input material characteristics. So, but in ANSYS or COMSOL supports import of material properties. So we will have option to configure that. So we have a very detailed, very thorough configuration dialog box in which we can do this. And then we have some CFD model exports for Fluent, OpenFOAM, Abacus, COMSOL, VTK, and MATLAB. We can also export non-uniform rational B-splines from the software, which is again very helpful when we are into generating implants, because in any tool, configuring on a NURBS model is much more easier because we get splines over there, and designing becomes very easy. And same thing, it is not very much possible with STL files. So yes, we can export NURBS format as well from here. So as I discussed in the first part, that we have scripting and automation once we are through with the workflow. So this can be in two things. First, we have a workflow. We have done some things, and then we are generating a script to do those things multiple number of times. Another part can be we are generating a script by our own using the scripter, using this scripting toolbox in the simpleware, and we can design from ground up using Python and some uh, predefined classes in the simpleware software. And we can generate the complete script to run a very customized workflow. So these are two types of workflows we can have. So let me just show you how easy it is to generate a script. So over here, what you see is the log. So these are some steps that we have performed on a data set. And in this video, you will see how we can convert it into Python script. So we just select the parts which we want to convert, right click and convert to Python. So this is now a Python script that we have, and I can save this part only and run this part multiple number of times on multiple data sets automatically. So this is also a very helpful part, which is good to have. We can incorporate our own APIs. We can build plugins for some repetitive tasks that we do. And you can work with simpleware team to generate plugins or a fully customized solution. So what fully customized solution means is from importing of data set, pre-processing, segmentation, CAD image integration, model generation. So all these things can be completely automated using some machine learning or AI tools. So those things also can be developed and incorporated in the software through the simpleware developer team. These are two broadly classified areas where simpleware software finds its application. So first is life sciences and clinical applications. Second is materials and manufacturing applications. So what we discussed earlier is same thing. We first import the data, then we do the visualization of our region of interest. Then we do the segmentation of our region of interest. Then we do measurement and analysis. Then, if required, we generate a model, even import CAD files to check to see the device interaction with the anatomy. And then finally, we can export it for 3D printing or model simulation purposes or teaching purposes. Surgical planning purpose can be also a thing. Uh, Many surgeons use models generated from these type of tools to prepare for a surgery beforehand, so that they can reduce the surgery time in the final OT. So this is something which is being done using medical versions of this tool. We have multiple modules in simpleware software. So what these modules are, these perform very different tasks, and based on requirement, customers select what modules they require. So I will discuss about each modules and processes behind it, and you will get to know what feature each module provides. Okay. So we have several modules. So our modules, some of the modules are fully automated modules that are AS Ortho and AS Cardio. We have CAD module for helping us to integrate our devices that we have designed into the software. We have a design link tool, which is specifically made for linking our software, that is ScanIP simpleware, with SolidWorks. So what it does, it makes the implant design experience seamless, and the import and export, the model is completely synchronized with SolidWorks. Then we have a FE module. So it helps us in generating meshes for a finite element or computational fluid dynamic analysis. We have export format. We have export capability of NURBS models. So here you can see we can export these kind of models as well from the software for maybe implant design purposes or multiple CAD purposes that you may have. We have some physics modules as well, some basics simulation we can do in the software. The tools are named as Solid, Flow, and Laplace. And let's discuss about these tools one by one. Just give me a second, please.
Sir, you are on mute, sir. Voice is not visible. Audible.
Ma'am, 1 second.
Okay. Yes, ma'am, I was on mute. Just one second. So I will just continue with my PPT now. Okay, another thing I would like to tell you is, although we are going to have a question and answer session at the end of this first session, in case anyone has any queries related to the current slide or anything like that, please let me know by unmuting yourself or sending your text in the chat box as well. So the first module is the finite element module. So in this module, we generate finite element meshes or for doing our finite element analysis or computational fluid dynamics. And this model offers the broadest range of image-based meshing tools and most robust meshing algorithms. So these are some proprietary algorithms, which I think we will discuss in the next session as well. And we can, as I showed you earlier, we have option to export in very specific finite element solvers as well. So those are widely used softwares in the industry in which we directly export. Then we have our NURBS module. So NURBS stands for non-uniform rational B-splines, and these models are widely accepted by various CAD packages directly. So using simpleware, we can generate our region of interest by doing the segmentation, and then further generate the NURBS model to export to CAD packages. These exports can be done in IGS or STEP formats, which are very widely accepted CAD file formats. Then we have this Cad module. So Cad module is an integration module. It allows you to import and position and do some kind of morphological operation on your implant. So this module will allow you to position, orient, translate your implant into the software to check the fit of it with the anatomy. We also have some internal structure wizard in this CAD module. So what that does is it helps you to generate internal lattices in your model, whether that can be in the implant or in the region of interest that you have just segmented. So that helps very much when you are going for 3D printing. It reduces the material required and also provides support for the external shell that we are going to print. So this is very helpful, this internal lattices. Some people who don't want to use the built-in internal lattice structure, they don't want to use the unit cells like gyroids, etc. So they can use their own equations for the unit cells and generate that internal lattice. So that is something we can do over here. So I have a few queries. Is this software open source? No, ma'am. This is a proprietary tool, commercial tool. Image registration, sir, we will, I think I will discuss it in the next session as well. So what in image integration, what we do is uh, in image registration, we register two different data sets of the same patient. For example, one patient has undergone a CT scan and an MRI scan. So both the modalities have their own properties. And in MRIs, we can visualize the soft tissues very nicely. And in CT, we can visualize the hard tissue very good, very much nice. So we can register these two data sets by providing certain landmarks, and that will give us a very good picture of both hard tissues as well as soft tissues to do the segmentation very easily in case of a complex segmentation. I hope that answers your query. Uh, Next query is, where is the use of CAD? So if you are asking about this CAD module, so as I said, CAD module is an import module. It only allows you to import and position, orient your implants in the software, and this and generating this internal lattices, which are very helpful in case of 3D printing as well as in finite element analysis. Yes, you can apply for the trial license. I think my colleague can provide you the link for that. We have an option to give you a 30-day trial license. So let's move on to the next module, that is the design link. So as I have said earlier, that design link is a module that is specifically to link or synchronize to provide a sync between simpler software and SolidWorks software. So as we know, SolidWorks is widely used in the industry for generation of custom implants. And so Simpleware has provided a link so that you can synchronize your models between these two tools. So uh, why do we need this synchronization when we can always go ahead and export the model as NURBS and then import in SolidWorks, do the design and come back with the model to check the fit? So this link is there so that this process is seamless. This design process as well as the process of importing and exporting becomes seamless. So we have some tools for synchronizing between these softwares. So what it does, you can start the SolidWorks project from Simpleware software itself, and then directly export the model. Let's say in this case we have a pelvic structure. So we can directly export this pelvic structure to SolidWorks like this, and then design an implant for maybe the acetabular cup or the femur implant. And then we can use the synchronize tool again to directly import this model, import this designed implant, custom implant into the model, and check the fit, whether it fits properly using some simpleware tools like maybe wall thickness or some measurement or analysis tools we can use. And we can also export the measurements as well from Simpleware to SolidWorks. So that is very helpful when we are going to design a custom implant. We have some simulation modules. So these simulation modules are not full-fledged EPI solvers, but we have some built-in EPI solver uh, to calculate, to do some kind of mechanical analysis on the on your model. It is widely used in materials and manufacturing application, but it can also find its application in the medical field. So the first module is the solid module. So solid module, as it says, it allows you to calculate your effective stiffness tensor elastic moduli, and you can model multi-phase materials to do the simulation on them using a similar boundary condition. You can do automatic calculation of best fit isotropic and orthotropic approximations to calculated effective tensors. So these are some outputs, some types of properties that we can get from the solid module. Then we have this flow module. So this flow module allows you to calculate absolute permeability of sample of porous materials, and these complete simulations are done by built-in Stokes solver. We can also visualize velocities and pressures along the porous material. Then we have a Laplace module. So this module allows you to calculate the properties which are governed by the Laplace equation, like effective electrical conductivity, permittivity, thermal conductivity, molecular diffusivity, and we have a built-in EPI solver for this as well. Now, this is a relatively new module, but a very helpful module for people who are working in large number of batches of data sets that can be a commercial application or a research application. So this is simpleware AS ortho module. So simpleware ortho module, AS ortho module is a complete auto segmenter for orthopedics. You can utilize its machine learning algorithms to automatically segment very key sections like hip, knee, and ankle. So right now, these three algorithms are provided with this module. So what it does, it will, if you have a hip CT scan, you can automatically segment and split your proximal femurs, pelvic, and sacrum, or as well as you can place you can place landmarks on pelvis, coccyx, and femurs. So placing these landmarks automatically helps you in getting very accurate measurements further. Similarly, we have option to segment the knee from CT as well as MRI scans. We can automatically identify femur, tibia, and associated cartilage along with patella and fibula. Again, knee landmarks are placed on femur and tibia. And recently, in the last update of this software, we got ankle CT auto segmenter. So we can again use the same machine learning algorithms to automatically segment our talus, tibia, fibula, and calcaneus from the ankle CT scan. We can place automatically place landmarks on ankle center, fibular notch, lateral, and medial malleus. This is a very good representation to show you how much time this segmenter module save. So here you can see on simpleware itself, an expert user has done the knee segmentation from an MRI in roughly about 40 minutes. And the automated segmenter did the same accurate segmentation within 3 minutes. So this is a huge time that is saved, which can be utilized for other high-value engineering tasks. Similarly, we have a AS cardio module. So this AS cardio module allows you to automatically segment your cardiovascular system. We can automatically segment anatomy specific models for hearts. This heart segmentation from CT scans includes left and right atriums and ventricles, aorta, pulmonary artery, and myocardium. Landmarks are automatically placed on multiple places like aorta and the left ventricle. This is again an illustration to show you. Expert user took around 4 hours to do the segmentation of this cardiovascular system, and this tool did it in around less than 2 minutes. So that is a pretty good amount of time that has been saved in this case. So this is the software overview. So right now we have discussed about most of these parts, which always starts with import. We have these multiple type of imports that we can do to the simpleware software. We can utilize multiple modules in the software to accomplish our task, whatever our end goal can be. It can be 3D printing, simulation, implant design, or anything else that can be diagnosis or surgical planning, etc. So then we get the final export of our region of interest or our analysis. Now we will discuss about some case studies using simpleware tool. So before starting the case study, we can take a 2-minute break if that's okay.
Okay, sir.
Okay, fine.
Dear participants, short break for 2 minutes.
Okay, So I think we can go ahead now.
Yeah, yes, sir.
So now we are going to discuss some case studies where simpleware has been utilized to perform some kind of uh, uh, analysis or simulation, or to identify, to find a solution to a problem. So the first case study is variability and accuracy of spine segmentation. So spine segmentation is considered to be a little bit complex than other parts because it contains multiple points where we have different vertebrae connecting together. So this case study discusses about how accurate is the model that we have generated from simpleware to the actual spine or actual vertebrae. How accurate is it? So uh, in this study, the effectiveness of manual segmentation of lumbar vertebrae, taking into account the proximity of articulating surfaces and degenerative joint changes. Simpler scan IP was used to generate these 3D models. The first step was performed in simpleware to do the image processing. So in this image processing, 8 cadaveric lumbar spine segments were cleaned of muscle and loose connective tissues and scanned in a CT scanner. These image stacks were then imported to simpleware software, and a complete workflow was done on it for doing the segmentation, and a model was generated. STL model was generated. Once that STL model was generated, so over here we can see we have our vertebrae, but these are all connected together. In the next step, um, these all vertebrae were segmented into multiple parts in each vertebrae separately. Once that was done, an analysis was provided for the quality of segmentation based on 2 observers performing the procedure twice on each specimen. These differences were calculated and by registering the surface model with an iterative closest point algorithm. Once this first part was done, the second part was to the 5 of the vertebrae of the cadaveric lumbar spine. 5 of the vertebrae were disarticulated from their neighbors, cleaned off all the soft tissues, and then rescanned separately and segmented without adjacent vertebrae and soft tissues to evaluate the original segmentation routine. So now we this in this project, the first scan that was done, in that all the vertebrae were completely connected, and in the next scan the vertebrae were completely cleaned. Here you can see, and then the segmentation was done for each vertebrae. Once that was done, once that was done, each vertebrae was compared with the vertebrae that we had segmented earlier, and RMS error value of below 0.39 mm was found. So this test therefore demonstrates the accuracy of models generated from CT images of the lumbar spine in simpleware software. It also indicates the potential of future studies involving patient-specific modeling of the lumbar spine. So this was our first case study. This case study can also be seen on this link. Next, second case study that I am going to discuss today is total hip replacement implant positioning. So implant positioning represents a significant challenge for total hip replacements. The position of implant is very crucial to determine the longevity of the surgery, and to also minimize the wear and tear, and to minimize the time that it will take for the revision surgery. So using this simpleware software, uh, simulation was done. Simulation, you can say, for the hip implant positioning, simulation was done. So in the first step, image processing, CAD integration, and finite element meshing was created. So simpleware software along with CAD and FE modules were used to do the segmentation of the region of interest, that is in this case femur, and importing of CAD implants, like over here you can see the implant, and positioning it properly, and then generating a finite element mesh like here. So the mesh that we have created here is contains both your implant as well as the anatomy. Once this mesh was generated, it was exported to ANSYS workbench, and a simulation was run on 425 successful simulation points with the Kriging regression method. The ANSYS workbench simulation was then able to use the RSM to the response surface model to determine the implant position that leads to the highest and lowest possible values of micromotion. These results can be interpreted by a surgeon to predict what best and worst position for an implant was. So in the results, you can see based on the surgeon's input, this position was considered to be the best and this position was considered to be the worst. So this automated tool was successfully developed with a simpleware software and ANSYS for combining image data and finite element analysis with the goal of analyzing interactions between the implant and the femur. With feasibility for the tool established, further work might focus on examining multiple implant designs and carrying out analysis on patient populations. The tool therefore has significant applications for surgical planning, in addition to implant research and development. Again, this case study can be seen on the following link. I have a query. The output from MATLAB in JPEG. So if you are exporting a JPEG format image from MATLAB, is that a stack of images or just one image? Because if you are
Single image, can it be taken in the same format to FEA, sir, in your software for modeling? Single frame format, sir.
What kind of analysis do you want to do on that model?
Using FEA, disk degeneration or herniation, that part has to be.
Okay, I got your point. So although it can be imported, the one single frame can be imported, but the finite element mesh elements that are tetrahedral elements are three-dimensional, and that would require the third dimension that we don't have in this case. So I believe if you have multiple stacks of images, like one after another, then you can import and very easily create a model, the finite element model here.
Okay, okay. Thank you so much, sir. And will this format support JPEG format will be supported in your software, sir? That can
Yes,
be
yes,
directly
import
given.
is supported, but we need to provide some more data because
More
the
data.
JPEG file doesn't carry the spacing information as well as
Only 2D
the
will be there.
yes, so it will not have that information. So we will have to put that information ourselves, like what is the spacing between two JPEG images. So that is something we need to put.
Okay, okay. Thank you, sir. Thank you.
Okay. Okay, so we can move to the third case study. So this case study is modeling of alternating electric fields for brain tumor treatment. So we may know that this TT field therapy is a type of electromagnetic field therapy to treat cancer, particularly recurrent glioblastoma. TT fields therapy delivers low intensity electric currents through arrays on the scalp and has demonstrated good results compared to the traditional methods. However, the precise distribution of TT fields within the brain and the extent to which they cover the recurrent glioblastoma remains poorly understood, and computational simulation from medical image data offers a solution for this problem. So simpleware software was used to generate models for this purpose. So what has gone on in this project, in this case study, is a patient was having this recurrent glioblastoma, and the correct positioning of the arrays was not being done properly. So the computer generated layout was used to provide provide the correct positioning of arrays on the scalp. So here you can see the tumor can be seen here. So the tumor can be seen in these two slices, and after 24 months, a new site was found for the uh, for the tumor. So this is a recurrent problem, and the primary tumor was still stable. Over here you can see. So for doing the simulation, we need the head model. So the mesh was generated for skull, dura, and the cerebrospinal fluid, our gray and white matter, ventricles, brainstem, cerebellum, the recurrent glioblastoma, as well as the transducer arrays. So these all models were generated in simpleware software and then exported as a finite element mesh to the COMSOL software, COMSOL multiphysics software. During the in the simulation results, the electric field distribution was studied. So here you can see over here, the analysis of electric fields in COMSOL software is done. High field strength is seen at the ventricular horns, and there is inhomogeneous electric field distribution on tumor. The new enhancement tumor is situated on the lateral border of the right lateral ventricle in an area with relatively low electric field. So it signifies that the position of the arrays, the electric field distribution is key to where the next tumor will arise. So this is what was studied in here, and based on the position of the transducer arrays, it was decided that the position, due to the position of the arrays, the new tumor has originated where significantly less amount of electrical field was distributed. So it provides us a very good idea about where to put the transducer arrays in the next project. So we have this next case study for 3D numerical foot model for running shoe design. So the case The case studies we are discussing today may not be completely related to your research area, but we are trying to cover uh, uh, to show you what different kind of industries or research areas can utilize this software to do. So earlier cases we discussed all about medical case studies. Now this in this case study we are going to discuss about human interaction device study. So this is a shoe. A shoe interacts with our uh, anatomy and it affects how we move around. So just give me 1 second.
Okay, sir.
Okay.
Yes, sir. Continue.
So this company is ASICS, which used this simpleware software to design a running shoe for a particular human anatomy. So this simulation saves times, cost, and materials, and ASICS use 3D computational models to better understand the role of stability in running shoes. Optimizing with simulation reduces the risk of lower extremity injuries for runners, as well as enhancing performance. So the sole structure and heel eversion angle are particularly important for understanding stability. Alongside experimental methods, models created in simpleware software for export to Abacus simulation tools help ASICs reduce prototyping times and costs as well as manufacturing waste. So what are the characteristics of the numerical model that we have? So this model is highly accurate multi-part 3D foot model, which is generated from a CT scan. So simulation in Abacus used to accurately predict the sole stability, and ASICS successfully updated sole design to improve customers' performance. This technique helped the ASICS reduce prototyping time, cost, as well as manufacturing waste. So again, the first part is always generating a foot model. To predict the shoe stability, a scan of the foot of a healthy female volunteer was obtained using the CT scan. The image data was imported to ScanIP simpleware software to build a 3D model prior to generation of the finite element model. So different parts of the foot were segmented. These are soft tissues, cartilage, ligaments, and plantar fascia, along with bones. The detail of the model enabled ASICs to be confident in the accuracy of their anatomical simulation. So here are the steps. So import was done, and then image segmentation was done, 3D reconstruction, and then finally the finite element model was generated. So Abacus software was used with the model to calculate deformation modes on polymer foam sheets with 3 different type of hardness. Results showed that good agreement with experimental testing as well, validating simulation as a way of enhancing existing ASICS methods. The numerical model was confirmed to accurately predict sole stability, leading to ASICs to successfully update the design of their soles to improve the performance of customers. So in this, we have compared the experimental as well as simulation results. And it was found that the simulation results were coinciding with the experimental results. So as a conclusion, Axis successfully created accurate, highly optimized models tailored to specific running conditions. The model is therefore valuable for SU stability designing, reducing prototyping costs and time, and skipping practical prototyping to improve sustainability. Okay. So at this point, does anyone have any queries related to the tool or anything that I have showed today?
Participants, now the resource person is open to questions. If you have any queries or queries in your research area or anything related to this 3D, now you may ask the resource person.
Yeah, the queries can be related to 3D medical imaging, like to understand how your workflow should be, or if any tool can accomplish this task.
Or you may write your questions in the chat box.
Sir, I have a query.
Go ahead,
Yes,
ma'am.
ma'am. Please go ahead.
Sir, is it possible to find the depth of why FE using FE analysis, the depth of effect due to spine in the spinal cord, sir? The depth of effect, how it has been affected, or how far the spine. Suppose we are considering the lumbar region segmentation, in that the disc degeneration or herniation has occurred. Using your software, will that be calculated, sir? How far the bones are affected?
Yes, ma'am. So a CT scan will show the internal features as well, and we can do the basic diagnosis in the import part as well. And once we have generated a 3D model, we will be able to see that bone degeneration.
The depth can also be diagnosed, right, sir? How
Yes,
far
yes,
it has been? Okay. Okay, sir. Thank you.
yes. So I will just, my colleague will just share you a link to the case studies. So if you go to that page, you will find a specific case study related to this query itself.
Okay. Let him share, sir. Thank you so much, sir.
Okay.
Sir, the participants are asking the link for the trial version. If it's possible, you can share it in the chat box, or you may guide them how to get the trial version of the software.
Okay. Okay.
And there is one more question in the chat box, sir.
Yes,
You
yes.
can.
I'm also checking that. So this tool is helpful in orthodontic cases. Yes, it is being used in those cases as well for orthodontic cases. So if you can be more specific, I can give you more details about it.
Sir, what are the input formats that the software will accept?
So what are the input formats that you can import in here, right?
Yes, sir.
Okay. So these are some of the import formats that we uh, support to import. Other than this, we can also import SolidWorks parts and assemblies as well for in case of implant design.
Participants, if you have any queries on the what are the different types of inputs that can be given, now here you can find the answer also. So next, sir, how this software will be helpful to the medical research people, that you please explain them.
Okay. Okay, sir, can you just repeat? I just missed some part of it.
If anybody is interested in doing research in this area, that processing the DICOM images,
Okay.
so you can guide them how to proceed or like that.
Yes, sure. So people with whom we work, so their research area includes designing of custom implants or checking the feasibility of custom implants to the research areas can be in the field of diagnosis, doing simulations on patient-specific models. So these are some of the research areas where this tool can be used. However, the research areas where it can find its application is very wide. Anywhere where you are going to be working with the patient-specific model, that can be there it can find its application. Other than that, if someone wants to do research in 3D medical image processing area, so that is very much, possible, and few research areas can be investigation of biomaterials, biomechanical properties. So these are some of the research areas where you can work in this 3D image processing. You can work on new materials development for implants. You can artificial implant of human organs. So these are some emerging fields where people are working in this research area, as well as um, the higher accuracy of CT image based 3D model for finite element analysis. So in mostly if you are working in trying to do your research in finite element analysis in medical domain, so this type of tool will be required for you to, and your research research work will require you to do the 3D image processing and 3D medical image processing accurately. So as accurate data that you have, as good quality data you have, it will provide you a much accurate output. And yeah, so research areas, as I said, it can be very wide. I mean, many application areas can arise from this basic thing, that is this 3D medical image processing.
I think we have the session on software also, no sir?
Yes, the next session we have.
Okay.
So in that, I will discuss about various tools that we have, and I may also discuss about some more export models that we can export directly from here. So I see I have one more query. Is it possible to integrate this software with other software like MATLAB, Python? Integrating, like if you want to export or import the models from here to MATLAB, yes, you can do that. Okay, so this page is open. So here you can see that this is the export formats that are supported. And here you can see the MATLAB is present for finite element meshing, as well as for computational fluid dynamics. So you can export your models from this tool to MATLAB specifically. And Python, so I also discussed about the scripting part. Let me just go back. Okay. So scripting can be done over here. So as I said, you can incorporate your own Python scripts over here, but configuring them based on the inbuilt classes that we have for Python. So you can import your own Python script and make some changes in it so that it is supported by simpleware, and then you can just run that to get your exact type of output. Another thing is export of Python script can also be done from here. So I also discussed earlier that we can export Python scripts so that we can run that task multiple number of times in this tool itself. So let's say my workflow utilizes a similar kind of data set I import every time. And my research includes uh, this analysis of multiple data sets for the same region of interest. In a case, it can be lumbar spine, to see how that lumbar spine injuries change in many patients. So that can be one of the research areas also. So I have multiple number of data sets, so I can automate some parts of that data set using other Python scripting. And the scripting can be done very easily. So over here you can see that this is the part that I want to automate. So I can directly select that and convert it to Python. So by this, I have a Python script with me, which I can utilize to run multiple times for every data set. Now just give me a second.
Okay, sir. Dear participants, we have the second session by the same resource person, where he will be demonstrating us the software.
So you asked about simpleware trial application. So here we can just search for simpleware.
Sir, there is one question in the chat box by Sumati ma'am.
Okay. Yes, ma'am. You can do the analysis of arteries in here. We have few case studies. Let me just show you through the website. So for application of applying for the trial license, we have this. You can go to the simpleware website and click on this get trial and go to request trial. So I think my screen is not. Okay. So this is the website for simpleware. And once you are on the website, you can click on this get trial option to request for the trial over here. So here we will just select simpleware and fill up our fill up this form. So once you fill this up, you will we will get the request, and we can connect with you to understand what are your requirements better. Other than this, I would also like to inform a few more things. So whatever I discussed today was mostly for academic section. So for commercial applications or for clinical applications, we the simpleware software also has FDA 5110K cleared and C marked. So what that means? So what that means that simpleware is FDA cleared and CE marked for to be used in point of care labs. And over here, going through the website, you can see that simpleware recently got its approvals for the medical version of ScanIP. So now it can be integrated in a workflow for providing end-to-end point of care solutions in the hospital itself in a clinical environment. Another thing was the case studies. So if you go to the simpleware resources, we have case studies. So I can click on life sciences and I have this. So some of the case studies are discussed from here itself. And you can take a look at some other case studies as well, whatever your research area is related to, or if you are looking for some research areas. So if you go through these case studies, you will get to know what different research areas this tool can be utilized, or what different research areas are there in this field. Okay, yes. So here you can go for application of a trial. Okay, so any more queries related to this application area, or anything else that you want to know related to this 3D printing, maybe 3D printing or 3D image processing? Please let me know. And this is what I had prepared for this session for today. And yeah.
Participants, if you have any questions, you may ask.
Sir, on this side. Sir, actually, I have a query. I have the data of CT scans of lungs. As you know, in CT scans, one patient have multiple slices, multiple images are there. So, if we want to know in which slice we have a particular disease or particular clot, is it possible to detect that by this software?
Uh, Diagnosis, I don't think you should use a tool like this, but what I can suggest you is you can generate a 3D model for that tumor or for the clot. So
Okay.
but yes, you can move through slices. I can show you in the next session how we can move through different slices. I think I have a data set for a lung CT scan as well. So I will try to show that.
Okay, sir. Thank you, sir.
Sir, shall we take a break for 10 to 15 minutes?
Yes. Okay.
Uh, Participants, we shall take a small break up to 11:15, and then we shall meet back at 11:20. Is it okay, sir?
Yes, that's fine by me, sir.
Participants, please respond. Is that okay with you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.